We now consider the main properties of the function determinant. Previously we have seen that the function determinant is the unique function satisfying the following three properties. The first one being multilinearity, the second one being alternating property, and the third one, the determinant on the identity matrix equals to 1. So we have seen these in lecture 7.1. Now let's consider a few more very important properties that are not defining, but they are implied by these three. The first one being that the determinant of a matrix equals the determinant of the transposed matrix. I remind you that the transposed matrix AT will have as rows the columns of A. Now to show this equality, we just have to recall that the expansion of the determinant by the Laplace rule can be carried on through any choice of row and any choice of column. The expression will change, but the resulting number will be the same. If we expand the determinant of A along any row, let's say the ith row, then we can expand the determinant of the transposed of A by the ith column. So since the ith column will be exactly the same as the ith row, and all the rows and the columns, the rows of A will become columns of transposed of A, we will actually get the exact same expression as expanding the determinant of A through the ith row. Therefore, this equality just follows from the fact that the Laplace expansion can be computed along any row and any column. The second property is that if A is a triangular matrix means that all the coefficients above or below the diagonal will be 0. So A, if it is triangular, then necessarily will be of the form written here, with the upper triangular region 0 or the lower triangular region 0. Then in either of these cases, the determinant of A will be the product of the scalars, of the coefficients on the main diagonal. Okay, so determinant of A will be A11 plus A22, determinant of A will be A11 times A22 times so on times A and N. Let's prove this fact by induction on the order n of the matrix. So let's assume that the matrix A has order n, and we have to settle the base of the induction. So let's start from the base n equals to 2 and see if the claim that the determinant of A in the case of triangular matrix is the product of the elements on the diagonal holds in this case. So let's fix, for example, the matrix A11 in 0 as the first row, and then A21, A22 as the second row. This is one of the two cases of triangular matrix we have written before. Now let's see if this is A11 times A22, which would be the claim. Well, we have the formula already for the determinant of a 2 by 2 matrix, and the formula is that the determinant equals the product of the first coefficient of the first row times the second coefficient of the second row. So A11 times A22 minus the product of the second coefficient of the first row times the first coefficient of the second row. So in this case would be 0 times 2, 1, which is 0. So we just have the first summand, A11 times A22, exactly as we wanted. So the base is settled. Let's see now induction step. Now the induction step involves assuming the statement for every matrix of order up to n minus 1. Okay, so we assume that. Now let's look at the Laplace formula which we covered in lecture 7.2, the previous lecture, apply to this general order n square matrix, which is triangular. So we will have all the coefficients above the diagonal that will be 0, and then any other coefficient is just randomly picked. Now, if we expand the determinant of this matrix along the first row, we will have that we just have one summand, because we just have one non-zero coefficient in the first row, namely a11, the first one, and all the others will be 0 by assumption. So the Laplace formula yields that the determinant of this matrix is going to be a11 times the determinant of this submatrix, the submatrix that we obtain deleting the first row and the first column, which is precisely this, the one I've written here, starting from A22. Now notice that this matrix is a square matrix. It is an n-1 by n-1 matrix, and it is triangular itself. Therefore, we can apply the induction step on this matrix and conclude that the determinant of this matrix is precisely the product of the elements along the diagonal. We have that this expression equals a11 times the product of all the elements of the diagonal of this submatrix, which is exactly what we wanted to prove. This is exactly the thesis of our statement here, statement number 2. Let's make first a preliminary consideration. We have that in general the determinant does not behave well on the sum of two matrices. In fact, the determinant of a plus b in general is not equal to the determinant of a plus the determinant of b. Strangely enough, though, if we consider the determinant of a product of two matrices, remember that the product of two matrices is very complicated to define, unlike the sum of two matrices. And we actually wondered why the product of two matrices had to be defined so in such a complicated fashion. The determinant of a times b is just equal to the determinant of a times the determinant of b. This is a theorem, and it is called Binet theorem. So as you can see, this is just what I've said. Determinant of a product of matrices is very well behaved with respect of the determinant. Now let's try to prove this. There are several proofs of these facts around, but there is a very simple one using the fact that the determinant is the only function satisfying its defining properties, the ones that we covered in lecture 7.1. So it is a striking application. The proof of this fact is a striking application of the defining properties of the determinant. Let's see how to use them. Indeed, from them it follows the following fact. Let f be a function from the set of n times n matrices, n by n matrices to R, and f an n multilinear and alternating function. Indeed, from the fact that these three properties, alternating, multilinear, and the fact that the determinant on the identity matrix is 1, we can derive the following fact. Suppose to have any function f from the set of n by n matrices to R, and this function f is n multilinear and alternating. So just the first two properties hold. Then we conclude that f applied to any matrix, any n by n matrix B, is equal to f applied on the identity matrix of n by n identity matrix times the determinant of B. So the function f is just fixed. Once we fix the behavior of f on the identity matrix, this just follows from the fact that the three properties, multilinear, alternating, and the fact that F identity matrix is 1, are defining for a function. So there is just a unique function satisfying all of them. We use this fact with the function defined as follows: f of a, f subscript a, we call the function fa, that goes from the set of n by n matrices to R and associates to a matrix B the determinant of A times B. So A is a fixed matrix and gives the name to the function f. So we fix the matrix A, and then fa is well defined, associating to a matrix B the determinant of A times B. So the determinant of the multiplication of B on the left by A. Now we have the following fact, that A times B can be written in form of column vectors, and the multiplication expresses well in terms of these column vectors. Indeed, any column vector of A times B can be represented as a column vector of B multiplied on the left by the whole matrix A. Okay, so we have A times B with this block representation, where BI's are column vectors of B. Now, expand the determinant along the appropriate columns, we can easily show that fa is n multilinear and alternating. So fa satisfies the property, the two properties, in order to conclude that it has this particular form when applied to any generic matrix B. By what we just stated, we conclude that fa of B, which we by definition is the determinant of A times B, so this term here on the left is the number determinant of A times B, equals the action of fa on the identity matrix times the determinant of B. But the action of fa on the identity matrix, by definition of fa, is precisely what? We have to take the matrix we are applying fa, multiply on the left by A, and then take the determinant. The matrix we are applying now, fa, is the identity matrix. If we multiply on the left by A, we get just A, and then we take the determinant of the resulting matrix. So this term is just the determinant of A. And since the real number here on the left-hand side, always by definition of fa, is the determinant of A times B, we have proven our statement, Binet theorem, which stated that the determinant of A times B equals the determinant of A times the determinant of B. A fundamental corollary of the Binet theorem is the following. So this is going to be the fourth property of the determinant. So if A is an invertible matrix, then we have that the determinant of its inverse is just 1 over the determinant of A. This fact alone implies that if A is invertible, its determinant is going to be different from 0. This is a fundamental fact of the determinant. Whenever the matrix is invertible, its determinant will be different from 0. Actually, it is true even the opposite. So if the determinant of A is different from 0, A is an invertible matrix. We will see this in later lectures. In order to prove this corollary, we apply Binet theorem to the following identity. We have that the identity matrix on the left equals, by definition of inverse matrix, A minus 1 times A. By Binet theorem, we get that the determinant of the matrix identity is 1. This is one of the defining properties of the determinant. But by this equality, the determinant of the identity matrix equals the determinant of A inverse times A. But by Binet theorem, this determinant is the product of the determinant of the two matrices. So determinant of the inverse of A times determinant of A equals to 1. And we can explicit determinant of the inverse matrix of A as 1 over the determinant of A. I'm going to end this lecture by considering the relationship between elementary operations and the determinant. Remember that elementary operations have been introduced in order to simplify the matrix through certain operations which left the rank of the matrix unchanged. As we noticed before, so the determinant is more easily computable if the matrix has many zeros. We have chosen, in a particular example, among the 3 columns that the matrix had, the ones with the highest number of zeros, because that to every zero coefficient corresponds in the determinant expansion a zero summand. Therefore, one might think that using elementary operations to change the matrix in order to make it have a lot of zero coefficients might be helpful in the computation of the determinant of this matrix. The only problem is that we don't really know how the determinant changes. At this point, we don't know how the determinant changes when we apply elementary operations. It might change very erratically, and we might not be able to find any concrete law that allows us to track back the value of the determinant if we know the sequence of elementary operations that we apply to the matrix. We are going now to analyze for each of the row elementary operations what happens to the determinant. The first one being switching 2 rows, any 2 rows of the matrix. The second one multiplying 1 row by a non-zero scalar. And the third one replacing 1 row by a sum between the same row we are replacing and the multiple of another row. Let's consider first operation A. The determinant is multiplied by -1. This is the statement, regardless where the 2 rows are in the matrix. To see this, notice that swapping Ri with Rj, let's assume that now j is greater than I, is the same as doing j minus I minus 1 consecutive swappings on Ri. So we switch the position of Ri with the closest row underneath I, j minus I minus 1 times, until we end up with having a matrix having in the jth row Rj, and in the j plus 1 row we have Ri. So this will take j minus I minus 1 swappings. If then we swap Rj upbound, after j minus I minus 2 consecutive swappings, we will end up with a matrix which will have in the as ith row we will have Rj, and in the jth row we will have Ri. Therefore, the combination of these consecutive swappings on Ri first and Rj afterwards will have as a result just the switching of the row Ri with Rj and leaving all the other rows of the matrix unchanged. Now, why do we split the switching of Ri with Rj with consecutive swappings? To consecutive swappings, we can apply the alternating property of the determinant. I remind you that the alternating property had an equivalent form, so see the end of lecture 7.1, and this equivalent form stated that if we swap 2 consecutive rows, then the determinant will be multiplied by -1. Okay, just one swapping means multiplying the determinant by -1. So if we sum in this case j minus I minus 1 plus j minus I minus 2, we will certainly get an odd number, because one of these two numbers we sum is certainly odd and the other one will be even. Therefore, the sum of an odd number and the even number will be odd, and we conclude then that the determinant will be multiplied by a coefficient that is -1 raised to the odd power, since we swap the rows for an odd number of times in this procedure. Raising -1 to an odd power will result to getting the number -1 again, and this concludes the statement that the determinant is multiplied by -1 in the switching of any two rows. The operation B is the multiplication of one row by a non-zero scalar. Well, this is just one part of the multilinearity of the determinant, so we already know exactly what the result will be performing this operation on the determinant. So the determinant will be multiplied by lambda. The third elementary operation involves replacing Ri, the ith row, by Ri plus alpha Rj for a certain coefficient scalar alpha and other row Rj. The statement is that the determinant is left unchanged by this operation. Indeed, let's express the determinant of the matrix to which we perform this elementary operation. We will write the matrix in terms of rows. The ith row is the sum of two vectors, namely Ri and alpha times Rj. We can apply the linearity of the determinant with respect of the sum, and we will get what? We will get that the determinant of these n vectors can be written as the determinant of, well, the first I minus 1 vector will be unchanged, then the ith vector will be picking up just the first summand, so Ri, and then the remaining vectors will be left unchanged. So this is going to be the first summand of the expression of the linearity of the determinant we are applying here, plus the second summand is going to be the determinant of the same I minus 1 vectors, and then in the ith position we will have alpha times Rj and then the remaining vectors. But the multilinearity of the determinant with respect of multiplication of scalars allows us to write the determinant of these n vectors as alpha times the determinant of all the remaining vectors we have here. But let's look more closely what are the remaining vectors. We have I minus 1 vectors which never change in this process. Then in the ith position we have the vector Rj, which is the one remaining here from the second summand. Then we have a certain number of unchanged vectors, and in the jth position we will have Rj again. Therefore we are in the situation in which the determinant, we are applying the determinant to n vectors, two of which are equal, one in position I and the other in position j. Notice that the determinant of these n vectors, the one appearing in the second summand of the expression above, is the same as -1 raised to the power j minus I minus 1 times the determinant of the following vectors, in which we have the two equal vectors, one next to the other. We just kept applying the operation A to these n vectors we considered before, this number of times, so j minus I minus 1, until this Rj vector will be in position I plus 1. Now we know that determinant of n vectors, two of which are consecutive and are equal, is going to be 0, and this is precisely the alternating property that we mentioned in the operation A. We covered this in lecture 7.1. Alternating property has been stated in two equivalent forms, the first one being precisely this. The determinant of n vector, two of which are equal and are consecutive, it is 0. So we apply in this case precisely this the property in this very same form. In conclusion, we have proved that the determinant of the initial n vectors are just equal to the first summand of this expression here. But you see, the first summand involves the determinant of vectors which are the initial vectors up to I minus 1, and then the ith position is just Ri vector, and then the remaining vectors. So these n vectors are precisely the rows of the matrix A. Therefore, here on the right hand side, I'm computing the determinant of the matrix A. And on the left side, we started from the matrix on which the ith row has been applied the operation C. We conclude, therefore, that the determinant of the transformed matrix is just the same as the determinant of A.